All right, I have just started the YouTube stream, and I'm gonna get started here. So let me just take a quick look. We got about maybe 8 people or so on Discord, and probably a few people over on YouTube. Cool. And it looks like everything should be working. I'm just looking at the volume level. That it may be a little bit lower than usual, but I don't want to clip it either. So if it turns out to be too low, let me know, and I will adjust the sensitivity of the mic. All right, so let's go ahead and continue with the exploration of the assembler. Okay, because we want to know enough about the assembler and also the processor in order to do the lab. Okay, so the lab will definitely be assigned later today. So what we'll be doing today is, at least for the first part, is to understand the concepts that you need for the lab. But along the way, we'll also kind of go through the whole processor again, with some different instructions. So that's what I have planned for tonight. What we'll do okay, so what we'll do first, okay, is to kind of look into some other instructions, because every time we go step by step, single stepping through the instructions, hopefully it will start to the concept will start to sink in, okay, and more importantly, I want you guys to understand how to ask questions. Okay, when you see that something, what leads to the next question, and then the next question, and then the next question, because that is reasoning, and that kind of knowledge or that kind of skill, goes beyond what I'm teaching just in this class. So that's one thing that I do want to convey, in my classes, not just this one. All right, so what we'll do is we're going back to the opcode table. The opcode table is a very concise summary of all of these various instructions of this particular processor. So what we'll do is, let's see, we'll start with, we'll work with another interesting instruction, and we'll walk through how the processor gets it done, and also the process to get the opcode into the processor. So our focus this time is this instruction. It is LD instead of LDI, which is the one that we talked about on Tuesday. So today we'll talk about LD, which is just load, and it has two operands. Okay, it has two things that the opcode or the mnemonic has to specify. So LD is called the mnemonic. It is the abbreviated, sort of user-friendly name of the instruction. The opcode of the instruction is 0111, and then a 4-bit bit pattern that is determined by which two register we choose to use in place of X and Y. What the instruction actually does is X equals to asterisk Y, which in C and C++ code means X is updated based on the value at the location that Y is pointing to, because asterisk Y is dereferencing Y in C and C++. So if you go back to the beginning of this particular spreadsheet, it says XX specifies one of the 4 registers. If register X is A, then the bit pattern XX is 00. If X is 1, then excuse me, if X is B, then the bit pattern is 01. If X is C, then the bit pattern is 10, and so on. And same thing with Y. So hopefully we are starting to understand how to read the opcode table. And now I'm going to switch over to the whiteboard for today's lecture. And what I'll do is, okay, I have to go find the window right here. Okay, so what we want to do is to specify and observe how the processor gets this done. Okay, so let me just go ahead and write what we want to get done. So let's just say that I want register C, okay, there we go, to get whatever register B is pointing to. Okay, this is what we want to do. And if you really want to be picky about the syntax, we can put a semicolon after that. Okay, so this is what we want to do. We want register C to get the content in RAM that register B is pointing to. That's what we want to do. So let me illustrate what I mean, just by taking a look at the RAM. Let's see, I think I have started the simulator somewhere, but I'm not finding it. Maybe I didn't start it. All right, so let me go find the command line prompt. Oh, okay, I see. Okay, so I don't know how many of you want to run this kind of code on the command line, but I think it's a good idea to learn how to do it from the command line, because at some point, using the command line to run the program is going to offer you, quite a bit of added features. So, even at this point, you can just kind of use the GUI. At some point, it is nice to do it on the command line. So I just started it on the command line, and it's complaining about a file not found. I just specified the wrong path then. Okay. There we go. 310 processor 0003. There we go. All right, so now we can see Logisim. And what I will do is to first zoom out, because we want to see all the components, or some of the main components. So let's just say that this time I want to put a random value at this location. And I want you guys to kind of practice how to read the RAM component. So can someone tell me what is the hexadecimal number corresponding to this location? I just want the address, not the content. So I'll give you guys a few seconds to do it, because I really want you guys to practice, right? So, with the highlighted location, the content is 00, but what is the address corresponding to this? And Daniel says 0E. Well, 0C is corresponding to this byte. This is 0D, and this is 0E. So Daniel is correct. The next one is 0F, but the one that I have highlighted in red is indeed 0E. Okay, so I'm going to initialize that content, that location, with a particular value, okay, which is sort of random. So I'm just going to put, maybe 9A into it, okay? So you just overtype, once you have a location selected, you just overtype, that location. You just type 9A on the keyboard, and that would change the content at that location of RAM. And now what I want to do is to set up the registers. So this is something that definitely needs a little bit of setting up, but it's mostly because we don't have the other instructions already explained yet. So this is going to be helpful to kind of dock to the whole thing so that it would do something like this. So what I would do, okay, so let's go back to the whiteboard again. So the whiteboard says, okay, not this one. So the whiteboard says I want B to contain the address. So that means in the simulator, I have to go to register B. Oops. In order to illustrate this instruction, that is. So I have to go to register B and change the content of register B to the address, which turns out to be 0E. Okay. And now that this is done, I go back to main. And I just want to know, how do I accomplish what the whiteboard is saying here? I want to take the content at the location that register B is pointing to, and then copy that content to register C in the register bank. So now what I need to do is to think about the pathways, okay? What needs to be enabled, and how do I set up a path to over there? So in order to do this, we need to think of a few things. So I'm just going to type, on the whiteboard of what we need to do. So the first thing we need to do is to enable RAM. So that means RAM cell, RAM select needs to be a 1. Now, every time we enable RAM, you have to ask the question, are we going to read from RAM or are we going to overwrite a location in RAM? Which one are we doing again? Just looking at the C statement, how are we accessing RAM? Are we overwriting RAM or are we reading from RAM? Daniel is correct. We are reading from RAM, so that means RAM load needs to be a 1. All right. So every time you either read or write, okay, with RAM, you kind of have to think about who is going to specify the address of the location that we are accessing, right? So before on Tuesday, we say, okay, we just need the program counter. Okay, we are using the program counter to specify what location in RAM we need to access. That needs to be done in the fetch cycle, and later on, it was also used in the execute cycle of the LDI instruction. But in this case, that seems different, right? We are not seeing star PC, we are seeing asterisk B. So that seems to me that we need to connect RAM.A. So I use this notation, which is object-oriented kind of notation, to denote the A port or the address port of RAM. And we somehow need to connect it to register B inside the register bank. So that is okay. Well, let's just look at all the overview first. Okay, so consider this an English writing class. Okay, we are just writing the outline first, and then we'll focus on okay, how do we actually get this done? Okay, so right now we're just working on the outline. All right, so now that we know how to connect the address port, the next thing is to think about the data port, okay? Where do we want to connect the RAM data port to? Well, eventually, obviously, we want to connect it to register C. And to be more specific, we want to connect to the D port of register C as opposed to the Q port of register B. Because every time we want to refer to the content of a register, we need the Q port. Every time we want to overwrite the content of a register, we need to present the new data to the D port. Okay? All right, so this is a pretty good overview. And then we switch over to Logisim, and we find that there's no easy path, right? Because when you look at let me just zoom out one more time. There we go. So when we look at the D port, or let's look at the A port first, okay? So we want register B to specify the A port, but the A port ends right here at a multiplexer. And register B is sitting somewhere deep in here. You go like, okay, that doesn't seem easy, right? So now that we know that the output of this multiplexer is the only way to specify the A port, because the A port doesn't go anywhere else, okay? It only goes to the output of this multiplexer. So we know that we have to configure the multiplexer to either use input 1 as the output, or it has to use input 0 as the output. If we look at input 1, then it goes like, that doesn't seem doesn't seem like what we want to do, because input 1 only comes from the program counter, okay? And there's nowhere else that it can come from. So that is not the answer. Well, since it's binary, so that means the correct answer has to be the other one. So now we say, okay, in order to do this, we need address mux to be a 0, because we have to connect input 0 to the output. All right, so I'm going to go back to the whiteboard because I need to document what we need to do. So we go back to the whiteboard, and then we just kind of document in order to specify, to connect the A port of RAM to the Q port of B. The first thing we need to do is to look at the address mux line and make sure that that is a 0. Okay, now we switch back to the simulator, and we go like, but darn it, it doesn't connect all the way to the Q port of register B. It just goes to a demultiplexer. Well, it's okay, because a demultiplexer is quote unquote programmable, which means you get to control, which output is connected to the input. So we can see that out of the two outputs, the one that we're interested in is output 0. So that means register output 1 demux should be a 0 because that specifies which output is connected to the input of this particular demultiplexer. So we now say, okay, you cannot see it because if I switch to the other screen, I would actually forget about the name of the tunnel. So I'm just going to type it first, and then we can switch back to the other screen. So what I'm typing is register output 1 DMX demux demultiplexer needs to be a 1. Okay, 0. It has to be a 0 because the highlighted line is coming out of output 0. Okay, and now we can track down to this wire. But before we go there, let me go back to the whiteboard, because I have just written down here, documented, that we need register output 1 demultiplexer to specify a 0. So now what do? We go to here and go like, oh, it's terminating at a component, but that's okay because we know the inside of this particular component, it is the register bank. So we right click on it, and then we click on view register bank. And then we say, okay, so far we have made the connection all the way to here. Now, how do we connect this wire all the way to the Q port of register B? Well, there's only one thing standing between those two wires because we are referring to this wire and this wire here. There's only one thing in between. It is called a multiplexer. So a multiplexer selects one of the input to connect to its only output. So we can see that this is input 1 that we want to connect to the output. And that selection is controlled by register output 1 select, because that wire connects to the gray dot, which is the selector of this particular multiplexer. Okay, so if I go back out, okay, this is corresponding to register output 1 select. So now I type on the side, register output 1 select should be 0, 1, but I'll just say 1, okay, because we can always just use base 10 number, because those values don't go up too much. So using base 10 or base 2 doesn't really make too much of a difference. Okay, so if I switch back to the whiteboard, you can see now that I have also determined that register output 1 select needs to be a 1. That completes, okay, switch back to here. That completes, what we need to do to connect a port of RAM to the Q port of register B inside the register bank. We're not quite done yet because we still have to connect the D port of RAM to the D port of register C. So off we go again, going to the map. So this time we are looking at this wire, the D port of RAM, and we are thinking, how do we connect that to inside the register bank, the D port of register C, which is what is highlighted at this point? That doesn't seem too hard, right? Because there's only one thing, in its way. So let's go ahead and try to figure that out. All right, so let's highlight the D port from RAM again. It is this particular wire, and we need that wire to connect to this wire over here. The only thing standing in between is a multiplexer, and this multiplexer is controlled by 2 bits. One bit is RIMux, which is selecting which input connects to the output, because this wire connects to the gray dot. The other wire, which is connected to a tunnel called RIEN, is just for enabling the multiplexer. So we need RIEN to be 1 to enable the multiplexer. Okay, so RIEN equals 1. I'm typing this on the side. And we also need RIMUX, register input multiplexer, to specify a 0 because we need to connect input 0 to the output. Okay, So that would accomplish the final connection here. Let's go into the register bank again and see what else we need to do. So we can see that whatever goes into the D port of register C also goes to the D port of register B, register A, as well as register D, because it's basically the same wire. And by the way, this type of connection topology is also called a multi-drop topology. Okay, so you have basically one source and it drops into multiple targets at the same time. So now we need to say, how do I single out register C so that only register C is updated when we have a rising edge clock? Because all registers would update on the rising edge clock, but there's an extra requirement that the enable has to be a 1. So now we have to focus on the enable of register C, which is this particular wire. And we ask, how do we make this wire a 1 so that the next rising edge is going to update register C and register C only, because we don't want the other registers to be changed. This wire goes into a decoder. A decoder is like a demultiplexer, where the input is always connected to a 1. Okay, that's basically what a decoder does. So we have 2 bits to specify here. One bit is the control bit, which is this particular bit over here. This one basically is just saying, should the decoder do something about the output? Because if this particular bit is a 0, which it is at this point, then all of the output of the decoder would be zeros. So we want this bit to be a 1, but that turns out to be RIEN. So RIEN is used to enable 2 different things. There is a multiplexer outside of the register bank that RIEN, or register input enable, is enabling. But there's also this decoder inside the register bank that the same signal is enabling. The other bit is called RIN cell. Now this is not a single bit pin, it's a 2-bit pin, because we need 2 bits to specify one of 4 things. So we see the first one is input 0, which is 0, 0 in binary. The second one is as output 1. I said input, I really meant output. The second wire is output 1, which is 0, 1 in binary. The third one is 1, 0. So we want register input select to be a 1, 0. So when we back out to the main circuit, that means RISEL, this particular wire, needs to be a 1, 0. So I go back to my whiteboard, and now we specify that. Oh, okay, I put the items into the wrong places. So these 2 items really belong here because they are helping me to connect the D port of RAM to the D port of register C. So we have one more item here, which is RISEL equals to 2 in decimal. And that's it, okay? So all we need to do now is to wait for a rising edge. When the rising edge happens, then the content at the location that register B is pointing to is going to update the content of register C in the register bank. Phew. All right, so let's get some questions. And Daniel is right on it. Good job. All right, so the question is, hold on, could you repeat the part about RISEL being 2? Because 1, 0 in binary is 2. Okay, so let's go back to the simulator. All right, so when we go into the register bank, 2 is in base 10. Yes, you cannot have 2 in base 2, remember. And if I were to specify something in base 2, I would probably do a 2 in parentheses just to emphasize it's a binary number. But yes, 2 is in base 10. So when we go into the register bank, we want this enable to be a 1, and that turns out to be output 2 of the decoder. And 2 in base 2 is 1, 0. And that's why this particular pin needs to be a 1, 0. If you look at the appearance of the chip, this signal is corresponding to the select. So to the outside world, it is the third pin from the top on the left edge. So when we go back to main, we just look up the third pin from the top on the left edge, and that is now our tunnel called RISEL. So that's how I know RISEL needs to specify a 2 in base 10, but it really is 1, 0 in base 2. All right. Okay, not a problem. Cool. All right. So now we have a pretty good idea of how to set up the multiplexers, demultiplexers, the decoder, and the registers, and the RAM, okay? But now the question is, but we can't really control those things individually because RISEL, RIEN, RIMUX, address mux, RAM cell, RAM load, those are all connected to the ROM. This is the ROM, but we can also call it the microcode ROM because every single location in this ROM is called, I call it a slice, but it is really a microcode, okay? The term microcode refers to code inside the code because we use microcode to implement opcode. So now the question is, what do we specify to get this done? Because, everything comes from RAM, and the content of RAM will get loaded into the instruction register, and then whatever is in the instruction register will serve as an index into the content of ROM, and then the output of that ROM location will then orchestrate everything so that we would establish the correct pathway to get things done. So now we go back to the opcode table and we look at this this row here, row 23. And we say, okay, we know what X should be. X should be C. We know what Y should be because Y should be let's see, register X should be a 2, okay, not 3. It should be a 2 because it is supposed to be register C. And then register Y is supposed to be register B. So XX needs to be as 1, 0, which is a 2 that specifies register C, and then YY needs to be 0, 1, which turns out to be just 1, which specifies register B. Do we have any questions about how I determine the bits of XX and YY? No questions? Okay. So XX needs to be 1, 0. I'm just typing on the side so that we can keep track of all of these things. Okay, so I'm almost done doing the editing on the side, and I will present that to the class when I'm done. All right, so it's done. Let's take a quick look at the whiteboard. So on the whiteboard, all I did is to write down what I said, which is the bit pattern XX should be 1, 0, which specifies 2 in decimal, which also is specifying register C. YY needs to be 0, 1 in base 2, which is really just 1, and that specifies register B. The prefix, which is the most significant 4 bits, is a constant of 0, 1, 1, 1 in base 2. So that means the actual opcode of LDC in parentheses B is 0, 1, 1, 1, which is the constant part, and then 1, 0, which is the XX, 0, 1, which is the YY in base 2. And that turns out to be 7, 9 in hexadecimal. So when I specify hexadecimal, I can use 0x as a prefix, because that is the notation in C as well, is whenever you want to specify a base 16 number, you use 0x as a prefix. So now that I know that is the opcode, I can just plug it into the RAM right away. I am bypassing the assembler because I am the assembler. I just assembled the opcode from the mnemonic. So now we go back to the simulator, and we'll just put it as the first instruction. So the first instruction is now 79 in hexadecimal, which is the instruction that we would like to specify. Okay, this is the instruction that will go to the location pointed to by register B, grab the content at that location, and then use it to update register C. All right, so we're going to execute this instruction using Control T. Okay, so this is going to be a slow process, but it is also a review for those of you who did not have time to review the material on Tuesday. All right, so Control T, but before we do the Control T, which is going to be a rising edge, we want to know what is going to be updated. Okay, so I'm just going to go through this really fast this time. So we want to look at what components are active. RAM cell is a 1, RAM is active. RAM load is a 1, which means we are reading from RAM. Then we automatically ask 2 additional questions. One is who is specifying the address port, and the second one is who is connected to the data port. The address port, we track it down, and the multiplexer says it's coming in from input 1, and there's only one thing at input 1, which is the program counter. So the program counter is connected to the address port of RAM. It specifies what location we should be reading. And then the D port is connected to many places, but of all the places that it connects to, only the instruction register is enabled at this point, which means when we have a rising edge, only the instruction register is going to be updated. So we can now expect that once I type Control T on the keyboard, 79 in hexadecimal is going to be the content of the instruction register. So I'm just going to go ahead and Control T, and there we go. Okay, so the instruction register is indeed updated to 79. This is called the fetch cycle when we execute an instruction. Now we are going to have a falling edge. The falling edge only updates the microcode pointer because that is the only register set up to update on the falling edge. So we know that it's going to be updated because the microcode pointer is always enabled. And now we look at the multiplexer leading to the D port of the microcode pointer. It is specifying a 1. The selector is a 1, which means we follow input 1 of the multiplexer. It's coming out of an adder. So that means when we have a falling edge, the microcode pointer will simply increment. So now we do a Control T, and sure enough, it just went from 000 to 001. And 001 has this new content. We're about to have a new rising edge. So once again, we look for things that are active at this point. We can see that RAM is no longer active. So that means, no matter what other pins are saying, that also connects to the RAM component, it doesn't really matter because the RAM component is totally dozing off and not paying any attention whatsoever. Okay, so RAM is out of the equation. It's not going to do a single thing. On the other hand, the program counter has its enable being a 1, so that means on the rising edge, the program counter will indeed be updated. So we want to know how it is going to be updated. We follow the wire connected to the D port. It's coming in from a multiplexer. The multiplexer has a selector specifying a 0, so we track down input 0. Uh-oh. There we go. Let me reshare the screen. Discord just crashed out. The good thing is YouTube is not affected by Discord crashing, and OBS, is extremely stable. I have never seen OBS crashing, so that's kind of good because OBS and YouTube, are super reliable. So that means everything that is recorded is also, always going to be there. All right, so getting back to here, the input 0 of the multiplexer, which is selected by the selector, is connected to the output of the adder. The output of the adder is just 1 plus whatever the program counter has. So we can expect the program counter to increment from 0, 0 to 0, 1. Okay, so now we have a control T, just like that. And we can see the program counter is now a 0, 1. Now we're going to have a falling edge. The falling edge only affects the microcode pointer, which is this one over here. So we track down the input. It's coming in from the multiplexer, but this time the selector is a 0. So we are using input 0 to update the microcode pointer. That connects to a merger, otherwise known as a splitter. The least significant 4 bits are always 0 because they're connected to a constant of 0. The most significant 8 bits are connected to the instruction tunnel, which is just the output of the instruction register. So whatever the instruction register has becomes the most significant 8 bits of the microcode pointer. So we can now expect the microcode pointer to update to 790 in hexadecimal on the falling edge. So control T right here, and okay, I'm switching back to, I'm looking on the side because I also lost the focus. Oh, okay, I see just sad and happy faces. Okay, very good. All right, so on the falling edge, we now see that the microcode pointer is updated to 790, and as a result, the content at location 790 in ROM is now presented to all of these various tunnels. We analyze the components again, and we can see the RAM component is active this time. Because RAM cell is a 1, we know we are reading from RAM because RAM load is a 1 as well. And now we have to ask who is driving the address port. We follow the address port through this wire. It goes to a multiplexer. The multiplexer has a selector of 0. We follow input 0 to the output of this demultiplexer. The demultiplexer has a selector of 0, which is okay. That's exactly what we want because we want the input to go to the output that we are now looking at. So we know whatever register is presenting its content to the third pin from the top on the right edge is the one that is, that's specifying the address port of RAM. So we go into the register bank and further track it down. So we are now tracking down this wire, and this wire, which is the output of a multiplexer, is connected to one of the inputs selected by the selector. The selector specifies 0, 1, so that means input 1 is connected to the output of register output 1, which is this Y over here. And now we have finally found out that, oh, okay, the Q port of register B is indeed connected to the A port of RAM. So that answers a part of the question, because the other half of the question is, what about the data port? Where is it connected to? Well, as usual, it is connected to a whole bunch of stuff, but the instruction register has the enable being a 0, so it's not going to update, no problem. It also connects to this demultiplexer, which can be dangerous, but the demultiplexer is disabled because the enable going into the demultiplexer is specifying a 0, so the demultiplexer is not doing a single thing. This wire also goes to input 0 of this particular multiplexer, but this particular multiplexer is, first of all, it is enabled, and 2, the selector is also specifying 0. So that means whatever content is on this wire is now presented onto this wire, which is connected to the output of the multiplexer. This is the top pin on the left edge. We go into the register bank, and we say, okay, where are you connected to? Oh, it connects to the D port of all 4 registers in the register bank, A, B, C, and D. But that's okay, because only one of them is going to update, because the decoder guarantees that one and only one of its output is going to be a 1 when it is enabled. The decoder is enabled. We can see this pin is a 1 because that also connects to RIEN, or register input enable. But we can also see the selector of the decoder is specifying 10, which is 2 in decimal. And the light green wire does correspond to output 2 of the decoder. So now we know register C is going to be the one updated based on what is on the D port of RAM on the rising edge. Whew, that's a mouthful. So let's do a Control T right now and see what happens. Control T, and we can see register C has just updated to a 9A. So we now go back to main, and we say, hey, that is the content at the location that we have just selected. Wow. Okay. So at this point, the processor has done everything that we talked about earlier, basically all of these things, and as a result, it is now getting this done. Okay, we are updating register C based on whatever content in RAM the register B is pointing to. But wait, it's not done yet, right? Okay, because we want to go on just one step further. So we go back to the simulator. A falling edge is the next one. So the falling edge is going to update the microcode pointer. The microcode pointer connects to the input of the microcode pointer connects to a multiplexer. The multiplexer has the selector specifying input 1. Input 1 connects to the increment, or the adder that increments. So we are expecting the microcode pointer to increment to 791. Control T, and it went all the way back to 0, 0, 0. But we explained this already on Tuesday, because at the end of the microcode sequence of every single opcode is the bit pattern to reset the microcode pointer to 0, 0, 0. So now we are ready to fetch the next instruction, or the next opcode in RAM, to be very exact. All right. Are we good so far? Okay. Am I boring you? Now you don't have to type it, because some people feel, they don't feel like, calling a professor boring. But if you feel bored because there's a lot of repetition, that resembles what we talked about on Tuesday, that's actually a good thing, because that means you already understand the material. This is not mysterious to you, and you already get it. The brain hurts too much to feel. That just doesn't sound right. It's hurting too much to feel. You mean to feel anything other than the hurt, than the pain. So if that is the case, okay, and I'm suspecting that that this is not just one person has that feeling. I'm guessing that is a shared feeling of a lot of people. So what can be done is to listen to the lecture again, but do it very slowly. Okay, do it very slowly. Every step that I explain, slow down, pause. Okay, if it's not clear why what I'm explaining is happening, you want to look up the documentation of a component. Okay, because if the confusion is coming from not understanding a component, how it works, then you can go to the help menu, and then go to library reference, and then look up that part, and then read the documentation. Now, if that doesn't help, okay. Oh, okay. I'll address that question just when I'm done with this. So if that is not helping, okay, you can set up an experiment just to play with one of a few components at a time to get a better understanding of how it works. Okay. So let me go address the questions, or the points in the text area, and then I'll come back and have a suggestion of what I mean when I said, play with a few components. All right. So the question is, why is it called processor 0003? It's because it is revision 3 of the processor design. Yes, I am planning to use 4 base 10 digits in this case. There will be at least a version 1000 at some point. And I'm glad that people find that at least one person find that re-listening to the lecture helps. I would not be surprised because I was told by several people, not just one, that the content of my lecture is concentrated. That was the comment. So that means when you listen to it again, but this time slowly, and also use the pause button a lot, you're basically diluting the concentrated juice. You're basically reconstituting your own apple juice from concentrated apple juice, which is good. And then there's the comment of, I wanted you to explain the differences between the architecture of the processor and something like you would find in an ARM or Intel processor. That is a good question, but I cannot really answer that question because I do not know. When I came up with the design of this particular processor, I came up with this design out of thin air. So it was not borrowed or inspired by something else. So from that point of view, I know it's kind of tricky because it may be very different from any known architecture. When is 0004 coming? Well, I don't know. At some point, I want to add the ability to have interrupts to this processor because it's a very important concept to explain. But right now, I cannot quite explain that concept. And also being able to kickstart it, that is funny. But at the same time, being able to save the flags register, is also very important, and that ability is also lacking at this point. So, yeah, Kickstarter, that is funny. Okay. So anyway, I have just explained one more instruction, basically how it works, okay? And you can see the process, okay? Let me go back to the whiteboard and I'll explain, the process, what I just did earlier, okay? So everything starts with what we want to do, okay? So what we want to do. So in this case, what we want to do is we want register C to be updated by whatever register B is pointing to. Why do we want to do that? Who knows, right? I mean, this is just an example. But that is what we want to do. And by the way, there is a term of looking at registers and then just specify how the content of one register is modified by something else. This language is also called register transfer. Okay. I think there's one more word to the phrase, but I'm fairly sure that register transfer is part of it. And it doesn't take long to find that because once I look it up, register transfer language, there we go, RTL, okay? So register transfer language is a specific quote unquote language to allow people to specify, things like processors, okay, to describe how something is done at a fairly high level. Because register transfer language, RTL, does not actually explain the interconnections of all the multiplexers and demultiplexers, the enable lines, the decoders, and whatnot. It really just explains what needs to connect to what, at a certain point in time. But it does have a name. Okay, it's RTL. Okay, register transfer language. So that's the first thing we did. Okay, the second thing we did was to look up the opcode table, find the bit pattern specifications. Okay, and once we find the pattern bit pattern specifications, which in this case is 0, 1, 1, 1 as the most significant bits, and then we have XX, and then we have YY. Then we quote unquote assemble by figuring out the variable bits. Okay. The variable bits, I use the term variable not because they correspond to programming variables, but simply because those bits are quote unquote yet to be determined based on which register we want to specify. So this reference to variable has nothing to do with variable as a concept in programming. Then we have the whole bit pattern, right? Then what we did was to update RAM with the opcode. So the opcode is basically a bit pattern. It is base 2 when we specify it, but by the time we want to update RAM, we have to use hexadecimal because that's the interface of Logisim. Okay, then we execute the instruction, right? So we then run the program by Control T. So Control T is really toggling the clock line. Okay, every single time you type Control T, it toggles the clock line. Toggling means if it's a 1, it turns into a 0. If it's a 0, it turns into a 1. That's what toggle means. So we quote unquote run the program by using Control T. And in that process, the first thing we did was a fetch cycle. Then the next thing is decode. So in between the fetch and the decode, there's also incrementing the program counter. Okay, but I'm only describing these things at a higher level. So fetch is really just saying, okay, go to the RAM location that the program counter is pointing to, grab that opcode here because that's what we want to. That specifies what we want to do. Okay, decode in my processor is really simple. All it does is to say, okay, use that opcode kind of like an index into an array. Okay, that's what decode is doing. And then the third one is execute. So in this case, the execution cycle is going to go to the wake up RAM. Okay, hey RAM, wake up. Yeah, we need you. And we want to read something from you. Okay, where do you want to read from? That register over there, register B is going to specify where to read. Fine, this is the content. What do you want to do with it? Oh, use this to update that other register over there, which is register C. That is the execute cycle. Okay. Then after the execute cycle, we just go back to the fetch cycle of the next opcode. And 0, 0 is the opcode of no op. So we basically can keep doing this and nothing is going to happen after this point. All right. So that kind of described the process that I just went through today. If there are no questions about what I just went through today, I'm going to talk about certain concepts in the assembler, particularly the concept of labels. Okay. So to illustrate the use of labels, I don't even need to type a program using an editor. Instead, I can do something. Let's do something like this because I can now introduce both concepts at the same time. One is the concept of a byte, which is not an instruction. It is known as a directive. Okay, so byte is a directive. And what it does is it requires an immediate constant. And if you just type byte and press the enter key, the assembler is not going to like it and say, hey, you need an immediate operand. So the immediate operand is basically just a number. Okay. So for now, we can just say that, okay, we'll just specify a number here, like 45. 45 is a decimal number. All numbers you can specify in as an immediate operand is a base 10 number. So we have byte 45. So now the question is, but what does it do? All it does, okay, byte 45, all it does is to tell the assembler and say, don't ask me what, don't ask me why, but I need this byte location to be the bit pattern representing 45 as a base 10 value. So you can now say, okay, what exactly is it? Oh, by the way, you can use // to begin comment on the line. So that's kind of handy. And it's also, this one I definitely stole from C++. So // you can now say, what is 45? 45 in decimal is 2 times 16, which is 32, plus 13, which is a D. So it is 2D in hexadecimal. So it's 0x2D. So byte 45 in decimal, all it does is to say, hey, this location right here, I want it to have the content of 2D in hexadecimal. All right, but wait, where is the location? We're always starting from location 0. In other words, if you imagine that you are the assembler, okay, but every time you start the operation, you're basically starting from location 0 of a book, okay? And as you read the lines, throughout the program, you're filling in, the locations byte by byte. So the next location is byte. Oh, let's pick something easy, okay? 64 in decimal. 64 in decimal is 40 in hexadecimal, okay? So now we have 2 bytes in this program. This is the byte at location 0, because remember, we always, when we start the assembling process, we always start from location 0. So the first byte that we specify is always the content of location 0. And since location 0 is now specified, the next byte is going to be, guess what? Location 1, right? So now we can go on, and you can intermix mnemonics as well as bytes. So I can put in an LDI instruction here. Okay, you can say LDI for 45, A45, and then you can have some more bytes, like byte 0, okay, and so on. So now the question is, what exactly is in this program then? Okay, we know the first 2 bytes already. What about the third and the fourth byte? Because an LDI instruction takes up 2 bytes, not just 1. So to assemble this manually, okay, we just kind of do what we have already done on Tuesday. So we have to look up the LDI instruction, and specifically, what do we specify when we want to update register A. So you go to the opcode table, you look up LDI, which is right here. So we know the most significant 4 bits are 0110, which is a 6, and then 11, that part is fixed as well. And then the 00 is the part that specifies whatever register we want to use. Register A is known as 00 in binary, so it is 1100 here. So as a whole, we have 6C for the opcode itself. So if I go back to the assembler, I can document it and say, okay, we have 2 bytes. The first byte is the actual opcode, which is 6C. And then the second byte is the immediate constant. Now that was illustrated on Tuesday as well. So if you didn't quite catch what we do with the second byte, you might want to watch the lecture on Tuesday again, but focusing on when we get to the ROM location corresponding to the opcode, you might want to focus on what we do with the program counter, because the program counter is specifying where to read in RAM, but at the same time, it is also auto-incremented. Okay, so that is the part that you want to focus on if you have a question of, how do we get this done? So 45 is 0x2D. So that would be location 2 and 3, because this is location 0, this is location 1, this is location 2, this is location 3, and this is location 4. Okay, so location 4 is pretty easy. It's just 0, 0. Okay, so I can do this manually, right? So I can just manually, now I can assemble the program, and I can see that we have 2D 40, 6C 2D, and then 00, in this program. You can check it in the RAM file too. So the RAM file is really just a dump of the content of RAM. So we can also see exactly the same thing, right? Because we can see 2D, 40, 60, 2D, and then the 0, 0. So when this is loaded into the RAM component, guess what? It's the same thing. 2D goes to location 0, 0, 40 goes to location 1, 6C goes to location 2, 2D goes to location 3, 0, 0 goes to location 4, and so on. Are we still doing okay so far? Do we have any questions? Okay. There are no questions. Oh, okay, here comes one. Line 3 does take up 2 locations. So those 2 locations are 6C and 2D. That is correct. So the whole program takes up 5 bytes because we have 1, 2, 3, 4, 5. But in terms of locations, we count from 0. So we have 0, 1, 2, 3, and 4. All right, cool. All right, so now that we kind of understand what is going on, which is the assembler really has a very simple job to do. We have to rewind back to location 0 all the time, every single time we start, and then it just reads the code in the source tab, line by line or row by row sequentially, and whatever each row produces, it will just say, okay, this is going to specify the next byte, this is going to specify the next 2 bytes, this is going to specify the next byte, this is not going to specify anything, and this is going to specify the next byte, and this is going to specify the next byte, and so on. Okay, so there might come to a time when you say, but I really need to refer to a specific location. Now that is needed when we need to jump, okay, when we need to say, okay, we want to continue execution not with the next opcode, but with that opcode way over there, okay? So the question is, how do we specify way over there? Well, you can do it by counting if you want to, okay, but that is a lot of counting, okay? So let me illustrate what I mean by that, okay? So let me just change the program a little bit, and we'll say, okay, this needs to be filled in later, and we'll say by this time, we would have, okay, we'll fill in later too with this one, okay? And by this time, we want to have register A having the content and then register B to have the address of where we want to update, okay? So I'm just going to comment here and say, by this time, we'll be ready to do this. And I cannot remember which one is which one, so I'm going to say that register A has the location and the register B has the content that I would want to use to update that location in RAM. Okay, and at this point, the program is going to stop. And on top of this, okay, I want this to be the content that I would use to update at the location. Let's see. Yeah, I want this to be the location to be updated. So I want this to be the location to be updated. There we go. All right. So let's try to figure out how to write this program, okay? Because all this program is going to do is to initialize register A, and then we initialize register B, so that, with this one over here, we are going to use register B, the content of register B, to update the location in RAM the register A is pointing to, and we are done. And the location that we want to update is the location right after the halt instruction. Okay. So, well, there's only one way to initialize our registers. The LDI instruction is the only way to put a specific value into one of the 4 registers. So that means, the first 2 lines would correspond to some kind of LDI instruction. Now, register B is only specifying what content to go into that location. So that one is pretty easy. It's just an LDI instruction. We specify register B to be updated, and then the immediate value is, how we want register B to be updated. So we'll just go ahead and say, 67. Okay. So 67 is the value that I want to end up over here. The problem is with the first instruction, okay? Because the first instruction, we know it's going to be an LDI instruction because that's the only instruction that we can use to initialize a particular register, LDIA, but we don't know where this one is located, right? So we can do some counting, okay? So we can go like, okay, put a question mark here. Yes, the assembler is not going to like it, but we'll fix it later. There we go. Yeah, see, the assembler doesn't like it. You guys have no idea how much time that I spend to do error checking in this assembler. Remember, this is a spreadsheet, okay? This is a spreadsheet serving the role as an assembler. Yeah, it was really fun, but at the same time, it's kind of convoluted. For those of you who want to know how everything is done, it's open sourced. You get to see all the formulae and also the custom they call it the custom functions under tools, and you can go to script editor. You can actually see exactly how the assembler is done in the form of a spreadsheet. But that's a story for much later. Okay, anyway, getting back to here. So I want to figure out what is the question mark going to represent. So you go like, well, that shouldn't be too hard because this instruction here takes up 2 bytes, so it's going to take up location 0, 1. This one is going to take up location 2 and 3. This one here, we don't know. This is going to take up location 5. So this is going to be at location 6. So you will put a 6 over here, only to find out that it is not 6, right? Because there's one more instruction that we have to specify, which is this one over here. So now you go like, oh darn it, I miscounted. This is supposed to be location 7 because we need to specify an instruction that we haven't talked about. It's called the ST instruction. So it's STA in parentheses and then B. And you can probably kind of imagine that this is the opposite of an LD instruction because you can see how the parentheses is on the other side. But when you look at the C notation, it is also exactly the opposite of an LD instruction. So now you go like, okay, let's do a count. Let's do counting. Let's count again. 0, 1, 2, 3, 4, 5. This is still 6. So 6 was actually correct. Okay. But what if I want to insert some additional instructions in between, here or here? Then it's going to throw off all the counting, right? So imagine you have an entire program written with these constants, okay? And every time you change that program, every time you remove an instruction, every time you add a new instruction, many of these numbers will need to be updated. Do you want to be the person doing all the update? I mean, it is not an impossible job. It's just it's a lot of chore. Okay, it's very tedious. Okay, now there are things that can help you figure that out because if you go to the Assemble tab, it kind of helps you because if we want this location, it tells us that this is location 6 already. Okay, because remember, column W tells us what is the address of a particular row. So we know the halt instruction is at location 05, so the location that is right after the halt instruction is location 6. So yes, you can use the assembler, use the Assemble tab of the assembler to help you figure out what number you should use to specify a particular location that you're interested in. But it is very tedious. Okay, so with this location here, I need to reserve that location. So every time you want to reserve a location for something, you probably want to use a byte directive. Now, in this case, it's really not important what value we specify here, but at least we are reserving this location, and the assembler knows that this location is used because we need to store something over there. Um, so the concept I want to illustrate here is the concept of a label. Okay, so instead of doing all the counting yourself and every time the program changes you have to recount, let's just use symbolic names. So I can use a symbolic name. The rules for a symbolic name is the same rule as an identifier in C and C++. In other words, anything you can use as a variable name or as a function name, you can use as a label name. It is case insensitive, so L1 all in lowercase would be considered the same as L1 in uppercase. So typically I use L1 with uppercase because L looks like a 1 if I use lowercase. So I can say this is label L1. So now the question is, what exactly does it do? Well, if you imagine the locations of RAM as a book, okay, not a textbook, but as a notebook, then a label is like a bookmark. Okay, that's all it does. Okay, it is just a symbolic name to refer to the address of whatever is following the definition of the label. So the definition of a label has a colon in it, to basically say, yes, we are putting label 1 right here on this page. Okay, how do we know the value of a label? Now, a label has a value. In other words, in this case, L1 is defined to be the address of the byte that we allocate using byte 0. So L1 actually as a label has a value of 6. Okay. Now, how do we know that? How do we look it up? If you go through all the tabs, there's a tab called SIMTab. Okay. Now I understand that why would you name a tab blah blah tab? Well, that's because SIMTab represents symbol table and not a tab in the spreadsheet. So that's why it's called SIMTab. But if you look it up, you will see something that's really kind of awkward. It's readable by human, but at the same time, it's kind of like, who would write something like this, right? So if you look closer, okay, okay, that doesn't work. Come on. There we go. So if you look closer, it is L1 over here, line number 4 refers to, and then open and end square bracket, RPN, and then inside square bracket, there's a 6, okay? And it says, address 6, error is nothing, okay? Well, some of you may notice, what this is, okay? If you have programmed in JavaScript, you might have encountered this type of notation. This is called JSON. No, not that guy in the movie, with a mask. It's JSON, Jason, son of J. Aiden is typing. Label table. Yes, label table seems to make sense. No murder time. Yep. JSON stands for JavaScript Object Notation. Very good. All right. So this is in JavaScript notation for a reason, but I'm not going to tell you. I'm not going to explain it because it's well beyond the scope of this class. But the bottom line is, if you look up this and you see L1, and then you see the RPN followed by a number, that is how a label is defined. In other words, this is how you know the value represented by a particular label. Now, it's no fun if you can just define a label and it cannot be used anywhere else. Okay, why would you want to define something that you cannot reference, right? Doesn't make sense. So we go back to the source and we now say, hey, I don't need to do my counting anymore. So instead of using a 6 over here, we can just say L1. Because what this does, okay, what the assembler does is it really just treats a label reference, like L1 in this case, as a number. It would just go ahead and look up what is L1. Oh, L1 is just 6. Then it would just put a 6 in the place of L1 in this case. So let me press the enter key. Everything is good, because if you misdefine something, or if you reference a label that does not exist, the assembler will know, okay, and it will complain and go like, oh, this is not going to work. So if I change this to label L2, which is not defined in this program, the assembler will come back and say unresolved reference of L2. Okay, so that's how it would, that's how the error is reported. So let's switch back to L1 over here. So now the question is, so what exactly is generated as the opcode or the bytes in this case? Well, to do that, you can go to the Assemble tab. The Assemble tab is really, really helpful if you want to understand, how the assembler works, okay? Because it really shows you the inner working, especially if you unhide all the columns from column B to column U. But that's a lot of stuff, so most people do not want to do that. So you can now see the first line, which is LDIA and then L1, really assembles to a 6C, which is the opcode of the LDI, and then 06, which is the definition of label L1. You go like, okay, that is kind of cool. Let's see if we can trick the assembler then. Okay, so when I said you're tricking the assembler, I mean, let's go ahead and define some more bytes over here, okay? And I want this byte to be the one updated by the ST instruction now. I want this byte to be updated by the ST instruction and not this byte anymore. Now, obviously, the easiest way to do it is to say, if I don't need to use L1 anywhere else, I can just say, let's get rid of this, move the label definition of label L1 all the way over here, right? And I don't need to change anywhere else in the program. Now, if we don't have the ability to use labels, then you're going to have to count again, right? But with the use of a label, we just change how the label is defined, and now the program should update. Now, how is it going to be updated? This is location 6, this is location 7, 8, this is location 9. So when you go to the Assemble tab, you can expect the LDIA instruction to change the immediate value from 6 to 9. So you go to the Assemble tab, sure enough, it is now a 9. And if you go to the Sim tab, the symbol table, you can see that L1 is now referring to a value of 9. Now, you also want to be careful because the actual value of a label is not based on the address. It is based on the RPN value. All right, so we are almost out of time, and I think this will give you everything that you need to do the homework. Even though I haven't really explained the ST instruction, but that's something I want you guys to figure out, okay? I want you to figure out, how the ST instruction works by Control T or, toggling the clock step by step and figure out how the pathways are established when that instruction executes. And guess what? You have the perfect program to understand the ST instruction too. The one that I have been talking about, this one here, is perfect for that purpose. Because when this program gets to the halt instruction, the result, okay, what you should see in RAM is this location, which is at location 09, would be updated to a value of 67 in decimal or 43 in hexadecimal. So when you run this program, okay, you have to kind of do a whole bunch of control T's, but by the time you're done with all the control T's, when you get to the halt instruction, location 09 in RAM should update to 43 in hexadecimal. So this program is not only here to illustrate how to use labels and what a byte directive is, but it is also here to help you, basically run your own experiment to find out, how the ST instruction works. Now, ST is really the reverse of LD. So since we just talked about the LD instruction today, if you ran this experiment sometime tonight or early tomorrow, okay, hopefully you still retain what we have talked about today, it wouldn't be too hard to track down how the ST instruction works. All right, so one more thing because I got 25 seconds left. So the question left here is going back to the symbol table. Okay, SymTab is symbol table. I borrowed these terms from compilers. Okay, because in the compiler you have a symbol table where it stores the definition of all the symbols like functions, variables, and whatnot. But the question is, what is RPN? What does RPN represent? Another character of another horror movie because it's Halloween. Tom is typing something. Nope, I'm not going to take road today, so no worries about road taking, but there is a code for the lab, so we'll get to that part. But before we get to that part, I want you guys to, okay, how about this? I get to that part, you guys will start thinking about what is RPN or look it up. All right, so the lab itself has its own code. I guess you can call this, a way of taking row. It's not exactly. All right, so let's see. All right, so the code of the lab is just LDI or lowercase, and it's due in, I'm gonna give you guys a week to work on this one, okay? Which also means it's gonna overlap with the lab that will be assigned next Tuesday. So there's flexibility, but it doesn't mean that you get a whole lot of time. Yes, so LDI or lowercase is the lab code. Today is the 22nd, so it's going to be the 29th when it's due. So October 29th, 7 p.m. So you got a week to work on this. And I certainly hope that you guys would kind of get started a little bit earlier instead of, like the few hours before it's due. Save and publish. So now you have it. Yes, R does stand for reversed. Yep, Tom is right. It is reversed Polish notation. Not sure whether reverse is reverse or reversed. I could be either way. Reversed Polish notation. Oh, okay, so it is reversed, not reversed. Okay, reverse Polish notation RPN is quite interesting because it is what we also call a postfix notation. I'm looking at the time. Today is Thursday. I know you guys are dying to get to Friday, so I'm not gonna spend extra time to explain what is RPN and its significance today. It is kind of fun. There are definitely interesting aspects to RPN, but I'm not gonna talk about it today. Eventually, we will talk about it because it really is an integral part of the assembler. But today is not the day because it's Thursday. We are already 3 minutes past the end of the lecture time, so I'm gonna let you guys go. Have a nice weekend, everybody, and don't forget to keep going. Okay, you gotta do some experiments in Logisim to really understand what is going on in the processor. And I will stay online for a little bit longer, so in case you need to uh, ask me about something, I will be accessible through the text channels. All right, so if I don't get to chat with you, just have a nice weekend, rest, and study at the same time. And then I'll see you on next Tuesday. Yep, thank you.